These meetings are about review. Well, I guess I can also do this. Say, hello, everybody. And we start with kinematics. Basically, the interpretation of graphs, just a couple things. Kinematics is what we're talking about for a while. This document, this number up here refers to the objective list that when you open it up, looks something like this. So you can kind of follow along. I know that was a request. Obviously, if anything needs to be approved or improved upon, you'll let me know, please. I've never done anything like this before in my life. Thank you for all being very adaptable to it. So we got to interpret some graphs right off the start. Position, velocity, and acceleration. That's nothing too ridiculous. That's something that we're fairly effective with. You begin to get that information early in your physics career. If you took Physics K, if you took AP Physics 1, this is something you spend a tremendous amount of time on. And, you know, that's the idea that we can do area, we can do derivatives, we can do slopes, and we can do integrals to various graphs. So if you were to get a graph, I don't know, let's say like this, where you had the velocity as a function of time, the College Board would expect that you could do a lot of different things from here. When you get a graph, you want to make sure you're taking into account all of the things that you can do to it. And the first thing that I would suggest that you do to a graph is read it. When we read this graph, we can see that it's a velocity versus time graph. And on a velocity versus time graph, I can now tell you that the velocity, what the velocity is at any point in time. So that's the first thing that you could get from it. With that information, then we could start doing a few more things to it. We could start figuring out where it is at a certain period of time. So in this case, we could take the area of the graph. And in this case, the area of this graph would tell us the displacement. And when I talk about the area of that graph, I'm talking bounded by the horizontal axis. We'll draw another example just to kind of give you an idea. Anything with a area above the horizontal axis would give you a positive displacement. It doesn't necessarily mean it's in the positive direction. It just means that it's gone towards the right in our standard nomenclature. Note that you would have to do 1/2 base times height. I know that this might be very much review, but it's always nice to remember those things. So we can take the area of this graph, and in this case, a velocity versus time graph, we would multiply the axes, noting that when we do velocity times time, we get displacement or a change in position coming from that initial idea of velocity is change in position over change in time. So we can read it, we can take the area, and the other thing that we could do is take the slope, and in this case, the slope would tell us the acceleration because we would do velocity divided by time, and we would get the acceleration, the rate of change of that. Okay, I divide the axes. Okay, so that's what they mean when they say interpret graphs. Can you take a position versus time graph and turn it into a velocity versus time graph, turn it into an acceleration versus time graph? Or could you take a velocity versus time graph, turn it into a position versus time graph, and turn it into an acceleration versus time graph? So that's the interpretation of graphs. They made specific note on the objective list to identify when one is positive and the others are negative or zero. So you could look here that say that the acceleration is positive, however, it's positive, but it's constant because the rate of change of this velocity is constant, the slope is constant. You could get lots of different graphs that you could look at this with. A common graph that would be useful would be for a vertical projectile, just something tossed straight up into the air, in which case we would get a velocity versus time graph that would start with something in the positive, approach zero, and then a negative. Noting here that we have a positive displacement and a negative displacement as we move on from there. We would note that the acceleration is negative, and we would see that there is a changing velocity, but we approach a initial value. When I'm introducing this concept to introductory students, I would say we're here, we're going fast. Here we're going stopped. And here we're going fast but backwards. And when I evaluate that, I start looking at it as, okay, this is positive. This would tell me that I need to have a positive steep slope on a position versus time graph. This would be about 0. Well, it actually is 0. And then this would be a steep negative curve. And when we take that information on an algebraic approach, we would be able to see that we get a position versus time graph that looks something like that. But then we would have to go deeper into our interpretation of graphs, where we would then perhaps need to do something with a function of time. So we need to be able to determine when these values are 0 from a graph. We need to be able to determine when they're minimums and maximums, which is something that are maxima and minima, which is something that you've been doing in your calculus class. You've actually been doing it in algebra class for years, where you find inflection points, etc. This is concavity change. Occasionally for an inflection point, you would find where the slope of one approaches 0 to determine a minimum or a maximum. Those are the things that you would start looking at it. So you would be looking for slopes of 0 to determine when this. You'd be looking for to determine when the value of the graph is 0. The other graph is 0. Yeah, I think that takes care of it with the slopes. But then we're dealing with only constant acceleration so far. So then we've got constant acceleration as right expressions, and then graph the position and velocities as a function of times, and then use the kinematics. So we could go through and derive them, but I've done that before. I'll go a little bit quicker than I have in the past to go through that. I always start with the velocity as a function of time as my approach. And I would look at something like that, where I have a increasing velocity as a function of time, but I do have an initial velocity v naught. I list that here, v naught. I list this here, vf. V naught just meaning the velocity at time 0. Occasionally that would be a plus c in your integrations from an acceleration statement. X naught would be the plus c if you were to integrate under a velocity versus time graph. To do this, I could do lots of different things. I could do the acceleration by taking the slope. And to get the slope of this graph, I would simply do vf minus v naught. And I would divide that by my time, the change in time from time 0 or whenever I wanted to the final time in this generic graph. It just looks like this. And then I'd find that to be the acceleration. We rearrange this slightly and we get our first kinematic. And that first kinematic that they like to give you is Vf equals V naught plus AT. So that's simply the slope of velocity versus time graph. That's the first thing that you would do to that. You should be able to use that given the appropriate values. You also need to be able to identify when the right kinematic is to be used. So I'm going to go ahead and write that first one over here. Vf equals V naught plus AT. The next thing that we would get is we would also need to be able to determine the position of the object at a particular time. So I would we'd be looking for delta x. Delta x here, we'd be looking at area. Did I write area? Oh well, I hope I wrote slope. I've got the area is going to be under here. When I do this, I hate trapezoids. I actually don't like trapezoids at all, but I see a rectangle and I see a triangle. To do the area of a triangle, I would do 1/2 base times height. And to do the area of a rectangle, I would do base times height. When I do this, I take the slope of this, or I just find the area of the triangle, and I say it is 1/2 times the base, which is time. And I take the height, which is VF minus VI. To get the base, the rectangle, I'm sorry, I would do, it's a shape, base is time, and the height is V0. To get the total area, I simply add those together, and I would say that my delta X is equivalent to 1/2 VF minus VI times T plus the quantity V0 T. Oops, that says initial, my apologies. To make the calculation that you would see on the College Board's formula chart, they say that this VF minus VI is also right here. If I were to move this V0 over to the other side, I apologize for switching my V0s and VIs. If I had VF minus V0, it would be equivalent to AT. So I can say that this quantity right here is also that AT. When I write my final statement, this comes from that, and I go delta X is equal to 1/2 AT. There's another T there, so that T times that T is T squared plus V0 T. And there's a second kinematic. They do it a little bit differently on the formula chart. So when I write that final one over here, I would show you what that looks like in that final form. They break this down into XF minus X0 to get that total, or that change of position, the displacement. The last one that we have is the one I typically derive from an energy statement. So I'll just draw another picture after I finish this one off. They do X equals X0 plus V0 T plus 1/2 AT squared. And there's two of the three kinematics that you'd be provided on the formula chart. I get them from this graph. You don't need to memorize them. You have a formula chart with you. I'm sure they're going to have one located on that document when you begin taking your AP exam that is administered digitally at some point in the future. I believe they're going to make those announcements April 3rd. We'll find out. The last one, I'm going to erase this here in a second. I get from standing on top of a building. And here I am standing on top of a building. In my hand, I have a ball. And the ball that I have is, I'm going to throw it down with some initial velocity. Let's call it V0. From our energy conservation statements that we've already used ad nauseum, if I was teaching an introductory class, I'd do this slightly differently because they haven't seen energy concepts yet, but we have. I would identify two forms of the forms of energy that it has, and I'm going to pick two locations. I'll pick location A, and I'll pick location B. And then I identify the forms of energy, excuse me, at location A, and it has K plus UG at location A, and at location B, it just has K, where UG is the height. And in this case, we'll just call it like a delta Y, change in vertical position, final minus initial, something like that. I then start talking about what I know. And I would say at location A, I have 1/2 mv0 squared plus mg h. I said delta y, but we'll just do h, it's easier. Note that g is a specific acceleration. This is just a nice constant 10 for us, although some people like that 9.81. And then I set that equal to whatever velocity it strikes the ground with, and that would be 1/2 mvf squared. Noting that the mass of the ball doesn't change along the way. For our system, we can eliminate the mass from it. We divide both sides by m or whatever. It reduces to 1. And then we algebraically solve for Vf. When I do that, I get Vf squared equals V0 squared plus 2gh by multiplying both sides by 2. As stated earlier, gravity is just a specific acceleration, so I make that change right here. And h is just how far it fell, or a displacement. So we can either call it a delta y, or we could call it a delta x. And that's the 3 kinematics that the College Board likes for you to see and be able to use. A lot of questions come up with how do I know which one to use given the problem. It's just what information do you have? Remember, you can only solve for an algebraic problem if you know everything but one of the values. We will talk about some system of equations that we could do, and we're going to get to a little bit of that today. Hopefully there's plenty of time to do that, but if we don't, we'll just have to do it another time, and that's okay. The next one that the College Board says is on the list is here, solving non-constant accelerated motion with differential equations. So we need to be able to identify velocity as a function of time and say a is dv dt. But I really think that is more along the lines of what is associated with this objective. When we have to determine drag and terminal velocity, we have to be able to graph it. We have to be able to do the differential equation. We have to separate and integrate, and then go back and determine what the a as a function of t is. So we're going to get to 1a, 1c, later in today's review session. But when we think of this, our most recent conversation over capacitors and RC circuits is what this is going to be most closely reflected like. I might actually make a separate video where we go something through that. I don't know. We'll see. I'm still trying to figure some of this stuff out. Okay. How is everybody doing? Am I going too fast, too slow? Am I audible? Before we move on to the next idea, just kind of a nice break right now before we get down to that. Thank you. I don't know about perfect, but we'll get there. So the next objective would bring us into projectiles in two-dimensional motion. Breaking down into components. Where is and how fast is a particle moving, comparing it to another location or particle. The common question that we do here is that football question, the soccer ball, where it kicks the soccer ball and it tries to figure out whether or not it goes over or hits the wall. you've done this. I think there's a quest problem about specifically kicking a field goal and knowing how tall the upright is using projectile motion. So we'll talk a little bit about that, but I'll also provide one of those problems for you to practice with, so that if there's any questions and comments, we can spend a little more time focusing down on that when it comes to our conversation Wednesday. So where and how fast is the particle compared to another particle? When I think of this idea down here, I really think of how is it when it's compared to a certain height or a certain horizontal position, comparing it to will it go over the wall, will it go under the wall, will it go above the goalkeeper's hand and below the crossbar, something along those lines, when you're solving that problem out. And then I wrote this down here, make sure you're aware of SOHCAHTOA. So your sine is the opposite over the hypotenuse, your cosine is the adjacent over the hypotenuse, and tangent is opposite over adjacent. You should also be reminding yourself of tangent. Theta is equal to opposite over adjacent, so we use the idea of secant tan or arctan to determine an angle when we're doing these problems. But we'll just start a problem, just a generic idea to think about this, to remind you of a few things as we do this. This can kind of be difficult because there's lots of things going on. You need to remind yourself of what's going on up and down is independent upon what's going on left and right. When it comes to projectiles, you need to know that it has a constant acceleration up and down of -10 or 10 down or -9.8, and it has 0 acceleration horizontally, and that allows us to understand which approach that we need to use. Oops, there goes my markers. So when I think about a problem like this, if I was writing a problem, which I don't often do, I would give you a V0 given at some angle, some projected at some angle, and that angle is generically theta. Green isn't as effective as I'd like. I might need to retire it already. We understand the trajectory of this projectile, and we're going to cover some of these other objectives. So we're also going to be doing something like this. We're going to be doing this one as well, where we graph it, we find the components, we write the expression, and we do some analysis to it. That's whether or not it goes over the hill before we get into Newton's laws. So pretty much this is just over projectiles for the next, I don't know, 10 minutes. Hopefully it doesn't take that long. We understand that the projectile is going to go something like this. Note that we're not worried about drag just yet. We would do some drag stuff only in the vertical. That's later in the review when we get to forces. So when we talk about relation to another particle, let's just say I have a particle here at some position x2, and it has a height of some value y2. So we just want to know whether or not this projectile would make it over that or below that. So we need to be able to describe its horizontal motion and its vertical motion as we go through this problem. So the idea that I would do to begin this process of solving it is, I would say, I'm just going to draw this generic diagram up here on the top right, so we have it for reference. Is I'm going to say that the horizontal velocity, the Vx, if you will, is equivalent to V0 cosine theta. Okay, that's going to tell me my horizontal velocity. We know that my horizontal velocity does not change in this problem. We don't have any external forces acting left or right. The only external force is acting down, and that doesn't look like down. That looks like down as we go through this problem. So we've got our Vx. We've talked about our horizontal motion. It's constant. Now, when we get to our vertical motion does have an acceleration. So I'm just going to call the initial idea of V0y, VOY. And then I'm going to say that is equivalent to V naught sine theta. But I know that this is undergoing the force of gravity. It's accelerating downward because of that the whole time. So we could talk about on the way up or on the way down. We just need to know that its initial velocity is in the upward direction and its acceleration vector is in the downward direction, which means we just need to set that up with something being positive and something being negative. So this is all about what's going on up and down. This would take care of writing the velocity as a function of time. So when I do that, we would be able to say that VF, V at any future time in the y direction would be equivalent to my initial velocity in the y minus the acceleration times time. The reason I have the minus sign here where I didn't have it before in our initial kinematic is because this initial velocity is pointing in the upward direction and the acceleration is pointing in the downward direction. An alternative approach that you might see, or you might be using yourself, or you might see in a book or in someone else's notes, is you might see something like this where they do it like that, where they put it out like that, although that looks a little bit more confusing to me, but it would be referencing what you might have seen before. Now that I have my velocity as a function of time, I can now do some calculus to that, or I can identify it as a constant acceleration formula. So I can either integrate this statement to determine the displacement in the vertical, or I could just use the kinematic that we saw before. And that kinematic that we saw before was delta y in this case, because we're talking about vertical motion, equals V naught yt minus 1/2 at squared. What this allows us to do is to determine the velocity at any point in time. We can determine the velocity at any point in time, and now we can determine where it is at any point in time. We don't know which time yet, but we know that we could figure out how fast and where it is at any point in time using these two statements with a combination of trigonometry from this right triangle that we drew and the kinematics. So how fast and how high or how low. When I go over here, I've got my velocity as a function of itself. It's just a constant. We know that there is no acceleration left and right. So the velocity at time 1 is equivalent to the velocity at time 2, time 3, at all times horizontally, so long as it hasn't hit the ground or another object where an external force has acted upon it. So we're going to take the black marker, and I'm going to start going over here, and I'm going to describe my horizontal motion of the object. Well, since I have a constant velocity, we know that delta x is equal to velocity, in this case, Vx times time. So based on the information that we have, we could then figure out how long did it take it to get to our original problem, x over 2, which we had drawn. I said, where is it at? How high is it at x over 2? So we would have to figure out, well, what time did it get to x over 2? Well, there's time, and I know how fast it got there. How far did it go? Well, it just went from the final position of x, it got to x over 2. It started at 0, and that equals Vx over t. Now we can determine what time it got to that point, x over 2. To do that, I can do x over 2, and I can divide it by Vx. And now I know what time it got there. Well, why is that effective? Why is that a useful thing? Why is that a useful process for us to go through? This time right here is now what we can use to plug into here to figure out how fast vertically it's going at that location in time. If I needed to know how fast is it going up and down at that location. Or in the question that I asked, would it go over that location y over 2? We could take this time right here and we could plug it in right here and right here as well, and we could figure out how high it is off the ground or how far it has fallen from its original position, whether it's a projectile that was shot horribly. If you're in an algebra-based class, you typically think of this as a very challenging problem where you project something off the edge and it falls to the ground like that. That is a very daunting problem for many. But if you just realize the horizontal velocity is constant, the acceleration is constant, which means we can describe all of the motion going on vertically with these two statements, and we can describe all of the motion horizontally with this statement. We shouldn't have any problem of identifying where it is vertically in relation to where it is horizontally on any of these problems. So those are the main techniques that you would use with projectile motion and thinking about what could I do to solve for those values and variables when it comes to given a position as a function of time, determine the velocities and components of the acceleration, or where and how fast a particle is compared to another particle. So where is it in relation to this wall that we're throwing the object at? And I'll repost that question on Classroom for the practice. I'll do that by the end of today for you guys to look at. So we can talk about them Wednesday after you get a chance to look at them independently or interdependently, however you guys set up your own ideas. So that's the ideas that I would associate there. I would say probably August and September, I didn't do as an incredibly effective job based on conversations that I had. But hopefully having it here will help you hone your ideas and think about it. Finally, any of this stuff, we want to make sure we're aware of those graphs. So we've got a horizontal, or horizontal. That's X, left and right. And we got vertical. That's our up and down, our Y stuff. So for our horizontal motion of a projectile, we would be able to talk about its position as a function of time, its velocity as a function of time, and its acceleration as a function of time. And when in doubt, draw a graph. That would be the idea in this first unit. Can I graph it? So the position as a function of time, well, it just gets farther and farther away from us at a constant rate. Why does it go at a constant rate? There's no acceleration. So I can go over here and I can fill in that no acceleration value. I know that the velocity is constant, so it looks something like that. Now, the generic idea of the vertical motion is, I can't say it's going to look like this every time. It will have this curvature, it'll have this shape, but it may not always start at 0 and it may not always end at 0, but our generic problem is that it starts at 0 and ends at 0. We'll get to why it looks like this shortly. I did draw it earlier in the presentation. We have our velocity as a function of time in the Y, where we define this initial point right here as V naught Y. And I wish I had thinner markers at this point. And then we get to the acceleration as a function of time, which we know to be a constant value of -10 or -g for our projectile motion problems. All right, so we have the negative slope that's constant. I can look right here and I can say, hey, it stops right at the top. That's a common conversation that you would have. The reason it stops at the top is because it changes direction. It was moving up, it slows down on the way up, it speeds up on the way down. Yeah, that's a fine statement. And then with a slope of -10. Where it stops kind of depends on where you're looking. In the problem that we did before, we would say that x over 2 is located somewhere right here, and y over 2 was located somewhere right here. And we could then say, well, it went up, and then it started coming down. And if you wanted to, you could break it down and start going, well, I could figure out how high it got, and I could figure out how far it got if I knew all of the stuff, which we did. We knew the velocity as a function of time. We wrote it down. We knew the position as a function of time as a quadratic. Notice as negative, that was the -1/2 AT squared. And then we also wrote down the position as a function of time. So if you really wanted to avoid any of the kinematics and just use graphical analysis, you can, because we could find this area and then we could subtract this area from it. If it were to continue to fall, all that would happen in the problem that I drew down here earlier, it would you just keep going like that down there, and then this would just keep going down like that, and all of these would, the horizontal stuff would just keep going. So nothing too elaborately different. You just got to know where you're looking. So you can define the time most effectively with this because it's constant, and then use that time over here. And that's my spiel on projectiles. I'm sure they can ask a lot of questions that combine it with simple harmonic motion or hitting an object at the top. I've seen a question where they do this. I'm not sure how they could do this based on the nomenclature that they've provided, but you can get to a problem where it projects something, it runs into a block right at its apex, and then like it has a collision, and then it starts to swing. So you do projectile motion, you'll do momentum, you'll do energy, and then you could do period, or you could graph the motion of this afterward looking sinusoidal. You could ask what time does it start from when it was launched, based on knowing that this was at some location x/2 and it reached it at its apex. I mean, it could ask lots of questions. But if you just go back to the ideas of the horizontal velocity is constant and the vertical velocity is accelerated because of gravity, you can start reducing the unknowns by solving for this one and then solving for that one at a time. If you look at it all at once, it becomes overwhelming. So just take it one step at a time. When in doubt, we get to the next idea, which is why things do what they do. And we get into what we would all say in my classes, write down F equals ma. So we'll get to this shortly. I'm going to go get a refill on my coffee. I will be right back. Whew. Okay. So I went through over the last couple of days and I read all the objectives and I broke them down to distill it into something a little less daunting than a list of all of that. So Newton's laws of motion just talks about, we got the idea of inertia, the tendency of an object to remain in its current state of motion, whether it's at rest or it's moving. And as long as there's no external forces acting on the object, it will continue to travel at a constant velocity, or, well, both are constant velocities, either a positive, negative constant velocity, or it will stay at a constant velocity of 0. That's what equilibrium is when there's no net force acting on an object. It can also be when there are forces acting on an object, but they cancel each other out. A typical example of equilibrium is just a box sitting on a table. So I have a box sitting on a table. We would then start drawing some arrows. The College Board would probably want you to identify quantitatively what those arrows look like, and they would typically give you some kind of grid like that. We've talked about that in class. But we would identify that we have the force of gravity, also sometimes given as the letter W, also sometimes written as mg. One of the common mistakes that, depending on how nerdy you want to be, sometimes people just call that gravity. Gravity is the acceleration because of the force of gravity. It depends on how much of a that guy you want to be. But the reason it's not going through the table is the normal force, and I list that as Fn. These two forces are equivalent to one another. It's an equilibrium. So how do we do that? We start by writing Newton's second law, which we know to be F equals ma, but we write the sum of the forces equals ma. I analyze the problem. I know that the net force up is equivalent to the net force down. So then I can say that the acceleration is 0, or I can say, let's prove it. If I want to describe this, I need to identify that one of these is up and one of these is down. So I would call this the positive direction. I'll call this the negative direction. It doesn't matter as long as you have opposites. I would then write Fn minus Fg equals ma. And since I know that Fn, in this case, the normal force, the force preventing it from falling through the table perpendicular to the surface, is equivalent to Fg, I can then say, well, this is 0. So this is 0. And you could prove it that way if you'd like. The typical approach that we take in my class is we just go Fn minus Fg equals 0. We know it to be an equilibrium, and then we would prove that Fn is equal to Fg. This is the typical approach for pretty much all of it. So when we talk about equilibrium, how are the forces? Well, when we're in equilibrium, we know that the up force is equal to the down force. The left force is equal to the right force. The in force is equal to the out force. All of them, the net, the sum of all of the forces in the vertical, the sum of all the forces in the horizontal, the sum of all the forces in the whatever you want to call this, the in and out, the z-axis. What about the velocity? Well, when you're in equilibrium, we know that the velocity isn't changing. So we would just say it's constant because we know that we're in equilibrium. All the net forces are equivalent to one another. Well, all of the net forces left equal all of the forces right. That doesn't mean that the left and right forces are equivalent to the up forces. It just means that the left equals the right, the up equals the down, and the in equals the out. What about the velocity? Since there is no net force, the acceleration is 0. Since the acceleration is 0, going back to those graphs, we say that the velocity is constant. Whether it's 0 or positive or negative, we don't know. It depends on initial conditions. So that's equilibrium. Then you get into this. How do forces change velocity? Determine the change in velocity from a force and determine the average force as a function of time. All of this stuff starts leading to me into Newton's third law, which also leads into how we would conserve momentum. So I'll get into some ideas about how we can how do forces change velocity, and then graph some of this stuff to take a look at it. So let's do it. So we begin with our idea of Newton's second law. Newton's second law telling us F equals ma. And we'll approach it from an algebraic perspective, but you could also substitute anytime I say delta with just a lowercase delta, which I would refer to in calculus space as d, as opposed to delta. Small changes. So F equals m delta v over delta t from our earlier interpretation, we talked about that's the definition of acceleration. It's the slope of a velocity versus time graph. Change of velocity over change of time would be a slope. Not to be confused with this m right here, which doesn't stand for slope. That stands for mass. What we would say here is, how do forces change velocity? Well, we would really want to make sure we're looking at all of the forces in either the vertical, the horizontal, or the, I don't know, the other one. So we put that there. We idea now that this is the net force acting on the object. I'm not going to keep this in my equation. And then we would just write down the impulse equation. F delta t equals m delta v. And depending on the net force and how long the net force acted on the object, we could determine the change of velocity of that object. The question is, well, what the heck if it's a varying force? Determine delta v from a force, even if the force is varying, was written specifically in one of these objectives in the objective list. So the most effective way, and the way I've seen the College Board do it, is they would give you a graph, or you would get enough information to get the graph. So if I had, ooh, squeak. I don't know, let's just draw it like this. We have time, we have 0, we have force. You would be given one bit of information, and that one bit of information would be the mass of the object. So let's say the mass of the object is m. And then we just say the force is varying. So there's a force that's not constant. It's changing as a function of time. You see at time 0, the force is small. At time far from now, the force is large. So can I use this information to identify the change in velocity? Well, we go back to the very first idea about interpreting graphs. So I wrote down read it, area, and slope it. I wrote it in those 3 locations for spatial reasoning, or spatial learning. So we had the read it. Well, what can I get from this graph? I can get the force at various points in time. If I take the slope of this graph, I get force divided by time, force divided by time, force divided by time. That's not what shows up here. All right, this shows force times time. But if I take the area of this graph, when I take the area of this graph, I get force times time, and that equals my mass times my change of velocity. So we could say that this value right here is the area. That's not to say that that's not divided by. I hope you're listening. If you're just watching, it'd be very tough, because that looks like force times time divided by area. But that is the area of this graph. So we get the area of that graph by going, I don't know, 1/2 times the force, right? In this case, since we have that force right here, 0, we could just say that's that force. Final minus initial, I don't know how you want to think about it, times time. That's the area of that graph. That tells us the impulse, the amount of force times the amount of time. But it also is telling us that it's equal to the mass times the change in velocity. We were given the mass when we did this problem, so we could do the area of this graph divided by mass, and that would tell us our change in velocity. So I think that would be an effective way to do that. They could also give it to you as a function of time. Well, if we had force as a function of time, would I take the derivative, or would I take the integral to find the area? And then you start thinking about, okay, well, I know that the derivative would tell me the slope. That's not effective. But the area tells me the integral, excuse me, tells me the area. So if I just had it written down in a number for it, like a force as a function of, if I just said f of t equals 3t, like that's all I had. Now that's basically what that is. But you would integrate to find that information out. So just something to keep in mind as you go forward, is you could integrate this side and set that equal to that as well. Area is an effective approach there. Note that you can't get the change of velocity unless you know the mass. So that takes care of, I think, that. Oh, you just do this in reverse. So if I was given the velocity as a function of time, I could talk about the delta V. Basically, I'd know this information. So I just need to multiply that times mass to get the average amount of force. So that's that. What do I have next? Yes, free body diagrams. Probably have about 15 minutes or so left based on what I'm on. Yes. So we got free body diagrams, F equals ma. We got to separate our components and do all that kind of stuff. So we could do a scenario where we have multiple dimensions to solve it with an object either accelerating or an object at rest. Let me think about a couple ideas. Let's just do something like this. This is an old AP problem. There's a helicopter. And it's got like a rope. And it's holding up cargo. It could be anything you want inside of there. Animal Crossing Nintendo Switches are located in this. Those seems to be a hot item over the last couple of weeks. So let's just say this helicopter is accelerating in the upward direction. And I want to know the tension in that string. How would I do that? Well, if I want to know tension in that string, tension is the force acting along the string. Kinematic is ineffective. However, a free body diagram is effective. So the object is accelerating in the upward direction. In order for this massive object to accelerate up, does the upward force have to be more than, less than, or equal to the downward force? And in order to accelerate up, the force along the string, which in this case is tension, would be more than the weight of the object. So this is a quick interpretation of a free body diagram under the influence of an acceleration. The reason it's accelerating up is the helicopter's doing something to it, but we're just isolating this part of the problem. We want to know the force of tension acting on this. We could do another thing, and I'll do an Atwood's machine or something like that for us to look at too, to break it down as well, if we wanted to, and we'll get to that with the idea of third law. They like you thinking about tension in terms of third law. I then say the sum of the forces is equal to ma, noting that this was given some mass. And I then say, well, what force is in the upward acceleration? The way I instruct my students to do this is I would say whatever the direction of acceleration is the positive direction. I identify that the force of tension is pointing in that same direction. So I identify that to be positive. I then say that this is acting in the opposite direction of the acceleration. So I would say that is negative. As a result, I would do Ft minus Fg equals ma. Given that I knew the mass of the object and the acceleration of the object, and I was looking for the tension, I would then say the force of tension, moving the force of gravity over to the other side, is equivalent to the mass times acceleration plus the Fg. You may be asking yourself, well, don't we have an unknown value here, the force of gravity? We don't. We just haven't made that final substitution. I didn't want to do too many steps at one time. Ft equals ma plus mg. And that's the amount of tension in the string. I've seen questions now where it takes this to a kinematic level, and I'll post it on the little homework or the problem set that you can look at just to think about do you know how to start each of these problems? Is an effective approach that you could use when I post those later today. But they say that the helicopter accelerates up, and it starts from rest, but it accelerates up for 5 seconds. After 5 seconds, it releases this string. How high does this box get from when it cut the string? So then you start going into some kinematic ideas or graphical analysis. But what we would say is it's a two-step problem. I'm just going to start give you a rough idea of how I think about it initially. Initially, we're just talking about the vertical motion of it. So I'm going to do the velocity as a function of time vertically. It doesn't have any horizontal motion. So I'm going to do velocity as a function of time. So while it's accelerating up, we know that the velocity would be increasing. It would approach more and more as time passed. The acceleration is in the upward direction. We said it started from rest. So I just say it does this. That would indicate as the helicopter accelerates up, while the tension is still in the string, we would be able to identify the velocity as a function of time, or we'd say that the acceleration of this is that way, just to kind of give you an idea of what's going on. Now, at some point in time, the string is cut. Well, with the string being cut, the only force acting on it is just the force of gravity. There is no more tension force. In our setup, we have defined positive as being upward. So notice that we have a positive acceleration right here. Well, at some point, the acceleration becomes negative. That's when we cut it. There is no more tension force. It is only acting under the influence of gravity, or the force of gravity, excuse me. So then at some point in time, it begins to accelerate down. Like that. Now, a couple things that the College Board likes to do, or any physics test would like to do, is to make sure you can interpret this graph effectively. So the question might be, when does the object return, or when does the object start going down? When does it begin to fall? It's not falling here. We know that. But a lot of people look at this point right here and they say, hey, something changed. They see the change of it going, they say something positive and they see something negative. Well, what we see is positive is the acceleration, and what we see here is negative is the acceleration. But it's still going up all of this time, and it's going up all of this time. When does it begin to fall down? Right here, when it crosses the horizontal axis. That's when it begins to fall. It's still gaining delta x positive. It's on its way up. It's still going up, 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 still going up. It stops. Then it begins to fall back down. So it's at its highest point here. Then it starts coming back to where it got. Notice this red line that I drew looks just like the projectile motion of an object tossed straight up in the air. On the way up, it keeps going up and up and up. It doesn't go, it slows down. It reaches a velocity of 0, but then it begins to fall. So it takes some additional time for it to get to its original state. So that's one thing to keep in mind as you think through this problem, that it goes up for a while after you cut the string. I'll give you some time to think about that as you go, because I think that's a common misconception. Another thing that I've seen, just to kind of backtrack a little bit, is it's like a 1984 multiple choice question or something like that. They give you a graph that looks like this. They say it's a velocity versus time graph, and they say, when does this object return to where it started? So it looks like this. And they go, when does this object return to where it started? And a lot of people like to pick this point right here. This is the most common incorrect answer. That's when its velocity is 0. But its initial position was here, whatever. We call it v x naught. Here, x is positive. Delta x, more delta x. It's going forward, going forward, going forward, going forward. All this time, it's going forward. Positive motion. All above the horizontal axis. It doesn't begin to go back to where it started until this point right here. It starts moving backwards now. So it doesn't get to its original starting point until some point over here. The way you would do this is you define this as delta x of positive by taking the area of this, and then you'd set this area equivalent to some area over here until you found that it was at its original location. So just some things to think about. The connections that you can make across the problems. But note that we have acceleration here, and that acceleration can be turned into velocity, which means we could determine the position and all of those things as we go farther and farther and back and deeper into a question. The amount of information that you can find is overwhelming occasionally, which is why we talk about where do I start. I got 3 pieces of paper left. This one describes friction. So we have friction, we have static and kinetic. I draw this picture that we've seen before. We know that all of this information right here is static, where the force of friction is greater than the applied force. Notice that the amount of static friction is variable. It's only enough. There is no fixed value of the static friction. There is a maximum value of the static friction, but it's not a constant value like we see in kinetic friction. Remember, we talk about this as being mu Fn, and in here it'd be mu S Fn, but it would only be enough. So the static coefficient of friction, you could describe as a variable amount, but it does have a maximum. Once I reach this point and I exert enough force, it would begin to move. The common discussion you'd have is what's the last thing you want to do while you're sliding a piece of furniture across the floor, and the last thing you want to do is stop. So that's the idea of friction, and then it talks about rough inclined planes, so we'll go through a problem like that. Everybody likes inclined planes, and I say that sarcastically. There's no facial expression because I'm only showing you this board. Well, I guess that's okay. I can rotate the paper. By paper, I mean whiteboard. We have angle theta here. I should have drawn this way bigger, dang it. So we have angle theta here. We say that it's rough. I put the mu. Say rough inclined plane. It's a U-Haul truck ramp. You could put a clock, although then you have to worry about a center of mass problems. Don't worry about it. We're not talking about that today. I've got a box sitting on top of this plane. I then break it down into a few things. This is where we get the idea of like a multiple dimension, multiple components, etc. I guess we could talk a little bit about circular motion. I don't have that on today's. We'll talk about that another time. I would then identify the forces acting on the object. I've got the force of gravity. I've got the normal force. And I should have done this a little bit longer now. I've got the normal force. I've got the force of gravity. And with nothing like nobody pushing it up the ramp, I look at this as only having a force of friction. Force of friction opposes motion. So it would be located in that dimension. Typically what we do, and I got to draw that out with machine. I told you drawing out with machine. When I think about this, oh, my son's got allergies. When I look at this, we don't see perpendicular vectors, right? We see that the force of friction and the normal force are perpendicular to each other, but we've got this force of gravity that's acting in a weird location. So what we got to do is we got to break it down into its component vectors. So I draw a vector that looks like this. That one is straight through the heart of the inclined plane. It's right along the line of normal force. These would be right on the same line. This would be one line. And then I draw this one this way. There's another way you could approach this. You could draw it in the opposite direction, where you draw the perpendicular component here and the parallel component here. All right, now we have to figure out what this theta is right here. But we know that this Fn is equal to that amount of force, and we would know the amount of force of gravity down the plane to counteract the amount of friction up the plane. So when you break this down, just to give you an idea of where we're going, we want to say the forces perpendicular to the plane, 90 degrees, equal to 0. It's not accelerating through the plane. However, the forces parallel to the plane, there may be an acceleration. So we say sum of the forces parallel equals ma. Okay. And we want to say here that the Fn component is equal to the Fg perpendicular component, which we need to define. We haven't defined that yet. And then we want to say here, we'll call downward. We'll think that it's going to accelerate this direction. So I'd say that we have some Fg parallel component minus the force of friction equals ma. So that's the approach that we got to do. I want you to be aware that in this diagram, this component triangle that I've drawn, they do not want to see this on a free body diagram if they ask you to do it. I just draw it there to help you identify where those forces are coming from. In this triangle that I've drawn, this imaginary triangle, as a former student referred to it as SKJ, we see that the hypotenuse of this triangle is the force of gravity. Occasionally, I observe students drawing this where the horizontal, this perpendicular line here is the hypotenuse, which ultimately causes ridiculous problems. So when I do that, I have to now figure out what that angle is. This one right here, these two are the same. Those two have the same angle. Spatial reasoning can tell you that, but you could also define this as phi, where phi plus theta is equal to 90 degrees. This is 90 degrees, and if this is phi and phi plus theta equals 90, then this has to be theta. I didn't like proofs in geometry because I like to make up my own ideas. I knew that right angles had 90 degrees. I'm sure that's a real thing. I don't know what it's called. Now that I've done that, I can now define this Fg perpendicular as Fg. That's the hypotenuse. This is the adjacent side of my right triangle. If I can't rotate it because I need to turn the paper over. This will be Fg cosine theta. And this one down here, I identified that one is too hard to read. This one down here is Fg sine theta, which allows us now to go over here. Circular motion is a different day. Okay. My brain started thinking banked curves. I don't want to think about banked curves until we talk about circular motion. Fg perpendicular we defined as Fg cosine theta. Ran out of space a little bit. That's Fg cosine theta. And Fg parallel is Fg sine theta. Minus the force of friction equals ma. Well, why is it important to do this? Why do we ever need to concern ourselves with the normal force? The normal force affects the force of friction being mu Fn. Fg sine theta minus mu Fn. Well, what's Fn? It's Fg cosine. And that equals ma. A couple things to think about. If the acceleration of this is 0, then that tells me that my coefficient of friction is sine over cosine or tangent theta, but the acceleration isn't 0 in this problem, so we could do a few more things. What we begin to identify is that the force of gravity depends on the mass times gravity, so I'm going to replace these F's. I ran out of space on this piece of dry erase. These become M's. We then identify that the mass is in every term, and the mass of the object sitting on the inclined plane is irrelevant. How the mass is distributed does play a role, but that's for center of mass stuff later on. And then we could say that the acceleration is equivalent to g sine theta minus mu g cosine theta, if you really wanted to do it. It comes from all of this and that free body diagram. Where would you be awarded points in this problem? By drawing this appropriately. Note that the FG needs to be the longest vector of all three of those. Identifying you have a component of them equivalent to 0, identifying what those components are, identifying that you have a dimension, I guess with dimension, components, component. The dimensions equal to 0 and one dimension equal to MA, then substituting and solving a lot of algebra going on in there. If the acceleration is 0, as I said earlier, if A equals 0, then mu equals tan theta. A common activity that you would do. How does the coefficient of friction compare to the back and the front of a calculator, the slippery side and the slick side? And you would take a board and tilt it and find the angle at which it goes. Always an enjoyable process for me as a teacher to watch people try to use a protractor correctly. There's that. Let's get to a couple more things before we call it a day. I'd like comments to let me know what would be effective in the future, what would be something to stop doing, what would be something to keep doing, and what would be something to start doing. But the idea of third law of motion, we see this the way it is depicted here. I would never describe it this way in my classroom. This would be a type of problem, couple different ways, a couple problems that come to my mind. Problem number 1. Sorry for the crude drawing, trying to do it quickly to respect your time. You've got that. We have multiple objects connected to each other. We would have to do something there. The other idea is a common problem that we see in multiple choice, and it frustrates us to all end. You have multiple objects being pushed here, and it asks you to identify the force from the second block onto the first block, or the second block onto the third block, or the third block onto the second block, etc. So a couple of ways that we do this problem in my classes, we would identify that this tension that is acting upward on this box is equivalent to this tension acting horizontally to the right on this block. And that's because for every action force, there's an equal and opposite reaction force. The amount of force acting through a string is constant. There is a problem in which case you may have a friction pulley. All of our problems so far are frictionless pulleys. If there was friction in this pulley, there would be a different amount of tension in these two strings, thus having a torque on this, causing it to rotate. We'll get to something like that in an advanced topic later in these presentations after we get a little bit of rotation. Another way you could do this is you could draw a free body diagram for each of these objects and then do a system of equations. That's what it means here, potential system of equations for multiple variables. You would be able to say that this tension equals this tension, and you'd be able to eliminate a variable. And you'd be able to say that this tension is equal to that tension, and you'd be able to eliminate a variable. The way we would do this in my class is we do FG1, FT1, FT1, FG2, FN, FT2, FT2, FG3. I would have my students align this all in a singular system. We would just pick which block is heavier. In this case, I need to do one more force. Let's say that this block is the heaviest block by a large margin. So we'd say the mass of 1 is significantly greater than the mass of 3. And as a result, the acceleration of this block would be that way, and the acceleration of this block would be that way, and this acceleration would be horizontally that way. As a result, we'd also have a force of friction that is opposing the motion, and then we do our sum of the forces equals ma statement, so crudely and roughly, F equals ma. We do Fg1 minus Ft1 plus Ft1 minus the force of friction plus Ft2, oops, I'll put minus Ft2 plus Ft2 my apologies, minus Fg3, and that equals m1 plus m2 plus m3 times acceleration. I got this Fg here, Ft, force friction, Ft, oops, Ft, Fg3. I didn't concern myself with these two forces, the Fg2 and the Fn, because they're perpendicular to the motion of the object. That's the idea of independence of perpendicular vectors. What I then do is I identify Newton's third law, which tells me that this tension and this tension are equivalent to one another, and this tension and this tension are equivalent to one another. This is more of a force diagram. I've been called out by some peers about this being a force diagram and not a free body diagram. There you go. You could be asked to draw each individual free body diagram for each of the blocks. You come to the same conclusion. And the algebra then takes place. The one substitution that you'd make is there's the force of friction right there. That's mu Fn. Mu Fn in this case, the Fn in this case is equivalent to Fg2. So that's how you would take care of that problem. And that would be multiple objects, tension, and a potential system of equations. For the other one, oh, and then to find each tension, I apologize, I shouldn't have erased it. You would isolate each block. So then you would just look at this block to find the tension. You know the acceleration now. So you'd say that Fg minus Ft equals ma just for that singular block. My apologies. Isolate it. The question that we could also do is we have a force here and a mass m, we have a mass 2m, and we have a mass of 3m. How are these forces taking place? So we would first define the acceleration, and we'd say that F equals ma, and then we would identify all of those masses. So I say F equals 1 plus 2 is 3, plus 3 is 6 ma. So the net force on the system is F over 6m. That's the acceleration of this block, that's the acceleration of this block, and that's the acceleration of this block. So then we could start identifying for every action force, there's an equal and opposite reaction force, which means the 2m block exerts a force on the 3m block to the right. Alternatively, the 3m block exerts a force of equal amount to the left. We can't look at both of these forces if we want to identify what one of them is. We're just going to look at one. So let's just say I want to know the amount of force acting on the 3m block. Well, the force that is acting on the 3m block is the force coming from 2m. That's the one in contact with it. So then I would say, what could I do? Well, I know that the force is what I'm looking for. I know the mass of that block is equal to 3m. And I know the acceleration of that block is right here. And I say that the acceleration of that block is F over 6m. Algebra ensues. Mass divided by mass. Those reduce to 1. I'm left with 3F over 6, which we know to be F over 2. So that F that is written here is equivalent to that F. So it's half of that F. Notice, if you like to think a little bit less algebraically and more logically, That's half the mass. It needs half the force to accelerate at the same rate as everybody else. That's the whole system. If you wanted to look at the force acting on this one, you would need to know a little bit more, because there are two forces acting on that one. The two forces that are acting on the 2m block would be the reaction force that we just identified. There'd be a force there, and there'd also be a force here. So we don't know what that force is. We would do something like this to find that out again. Actually, we have enough information. My apologies. We need to find out what this force is. So we'd say we have a force pushing it to the right minus a force pushing it to the left. Yeah. And that equals that equals 2m F over 6m. So the net force acting on that block is 1/3 F. There you go. Which means that we would put 1/2 F there, 1/3 F there, 1/2 plus 1/3. 1/2 plus 1/3. 2/3. No. Yes? No. 5/6. I guess. Maybe I'm wrong. I apologize. Drag and terminal velocity graphs. Differential equations. Separate and integrate. Determine A as a function of T. That's the last thing that's listed in the first two sets of ideas. We'll just do a rough idea, and then on Wednesday, I'll go through it a little bit more detail. You have an object, I don't know, a parachute, coffee filters, what we did in class. We have the force of gravity. We have a drag force, but the drag force depends on the force of gravity. It might say it's, or the drag force depends on the velocity. So we might say that the force drag is equal to negative BV or something like that. It'd just be something depending on the velocity. The first thing that it would ask you to do is find the terminal velocity. Well, a terminal velocity, FT, VT, excuse me, the terminal velocity is when happens when A equals 0. So when does A equal 0? Well, A equals 0 is an equilibrium problem, so that's the force down is equivalent to the force up. So we do FG minus FB equals MA, where A is 0. And then we do FG when FG equals FD. When does FG equal FD? So we do MG equals negative BV. Actually, we just do whoop. And then we do mg over b equals v for our terminal velocity. That's the first question we do. It'd be an equilibrium problem. Well, what's happening to it while it falls down? Well, if let's drop it initially, it would start slow. Let's just draw a velocity versus time graph. You'll see this looks similar to what we, like the last thing we did before spring break. The velocity of the object as it falls, I'll pick down as the positive direction. For me, that's what's happening. It's falling down. The net is down. So I think of that as the positive. You could see it in the reverse order if you wanted to. But it starts with a velocity of 0. And I know that it will ultimately reach a velocity of mg over b. Remember, that's our terminal velocity. So that's what's going to be right here. It's going to approach that. So just an idea of thinking about what the shape of this looks like, and then you can reference your RC circuit notes to see what we will be talking about Probably Wednesday we'll spend some more time. It is a lot of information. It's been a lot of your time. I apologize. It would approach that value. And what you should be realizing is that we're going to have to do a differential equation, and the differential equation is going to ultimately end with a natural log statement. To get what that would be is we do FG minus BV. That's what we defined F, actually, let me just, if I'm gonna get all the way there, we do MG minus BV equals MA. But we've got to identify what A is, and A is dV dt, much like our dQ dt was for current. And then you can start seeing that we have to go through a separation of variables, and then we'll have to integrate as we move forward to get to something like this. I'll write some papers out so you can see all those still images, but it would be a lot to go through, and I know your time is I've asked for an hour and a half. So I'm gonna end it there, but you can start to see that's exactly where we got with our V minus IR minus Q over C stuff that we were doing before. I hope that you all have a wonderful day, and I hope that this was effective for you. I will look forward to seeing all of you at some point in the future and watch you walk across the stage graduating. Have yourself a great day, and if you have any questions, I'll sit around here in the chat for a minute, but that's the end of the presentation for today. Have a wonderful one. Have a magnificent Monday.